Hello dear friends, welcome back to my YouTube channel Chemistry Aspirant. Now in today's lecture we are going to learn about some challenging and interesting example to predict the type of hybridization of an atom in a molecule. So in the previous lecture we already studied about how to predict the type of hybridization of an atom in a different molecules. The link is given in the description box. Kindly watch that video also. So now let us consider the first example, that is carbonic acid. So its molecular formula will be H2CO3. I have already shown the structure of the carbonic acid. The central atom in the carbonic acid is the carbon atom. Now let us consider the electronic configuration of the central atom: 1s2, 2s2 and 2p2. So here you can observe that 2s and the 2p atomic orbital contribute to the valence shell. Hence, the number of electrons that are present in that atomic orbitals are considered to be the valence electron. Hence, the total number of a valence electron in the carbon atom will be equals to 4, as the 2s contain the 2 electron while the 2p also contain the 2 electron. Let us consider the total number of a atom attached to the carbon atom. So here you can observe that the one oxygen atom is bonded with the carbon atom by the double bond, while the two oxygen atom attach to the carbon atom by the single bond. So here the total number of a atom directly attached to the carbon atom is a 3. Here you have to remember one important point, as the one oxygen atom forms the double bond. Hence, out of the 4 valence electron, 2 valence electron are used to form this double bond by the oxygen atom, while the remaining 2 oxygen atom form a single bond with the carbon atom. They use only a 1 electron. That means each oxygen atom use a 1 electron. Hence, here the total valence electron used for the formation of carbonic acid is a 4. So the total remaining valence electron will be equals to 0, as the central carbon atom contain only 4 valence electron. They are used to form this bond. So the remaining valence electron on the central carbon atom will be equals to 0. As the remaining valence electron is equals to the 0, therefore the total number of lone pair of electron on the carbon atom will be also equals to 0. The formula for deciding the type of hybridization. So here you know that we use a simple formula in which we find out the total number of a atom attached to the central atom plus the total number of a lone pair of electron on the central atom. So in this example, the total number of a atom attached to the central atom is a 3, while the total number of a lone pair of electron equals to 0. Therefore, this number comes to be 3. If the number is equals to the 3, then the type of hybridization for carbonic acid sp2 hybridization. So this is a simple first example in which we have observed that the one oxygen atom contain the carbon oxygen double bond. Hence, the 2 electrons is utilized by carbon to form the double bond. So this much point you must remember while considering this as a challenging example. Let us consider the second example. Here I have taken the Xenon Tetrafluoride molecule. So its molecular formula will be the SX4. The central atom in the Xenon Tetrafluoride molecule will be the xenon. So if we consider the electronic configuration for the central atom, that is xenon, that will be equals to krypton 36, 5s2 and 5p6. So 5s and 5p contribute to the valence shell, and the electrons that are present within the 5s and the 5p will be the valence electron. Hence, the total number of valence electron in the central atom, that is in the xenon, will be equals to 8. Now, the total number of a atom attached in the Xenon Tetrafluoride molecule is equals to 4, as the 4 fluorine attached to the central xenon atom. Now, the total number of remaining valence electron is equals to the 4, as you know that each fluorine atom will use a 1 electron of a xenon to form the xenon fluoride bond. Hence, out of the 8, 4 electrons are used to form the xenon fluoride bond. So the remaining valence electron on the xenon will be equals to the 4. Hence, the total number of a lone pair of a electron on the xenon will be equals to 2, as it contains the 4 remaining valence electron. Therefore, there will be the 2 lone pair which is present on the xenon atom, because we know that each lone pair contains the 2 electron. Here, the type of hybridization is decided by the total number of a atom attached to the central atom plus the total number of a lone pair of electron on the central atom. So, in the xenon difluoride, here the total number of a atom attached is equals to 4, while the total number of a lone pair electron is equals to 2. Therefore, this number comes to be 6. Therefore, the type of hybridization of a xenon in xenon trifluoride is equals to sp3d2. So, again you can cross verify this number. You know that in this molecule there is a 1 s atomic orbital used, 3 p atomic used, and the 2 d atomic orbital is used. So, 1 plus 3 plus 2, total will be equals to 6. Let us consider the third example, that is xenon hexafluoride molecule. So, the molecular formula will be the ZeF6. Here, the central atom in the xenon hexafluoride molecule will be the xenon. Now, let us consider the electronic configuration of this central atom. Xenon atomic number 54. So, its electronic configuration will be the krypton 36, 5s2 and 5p6. So, again 5s and 5p contribute to the valence shell. Hence, the electron present in the 5s and 5p will contribute to the valence electron. So, the total number of valence electron in the xenon is equals to 8. Again remember, the total number of a atom attached in the xenon hexafluoride molecule is equals to 6, as the 6 fluorine attached to the central xenon atom. Now, the total number of remaining valence electron will be equals to 2, as you know that 6 fluorine attached to the xenon atom. Hence, they will use the 6 valence electron out of the 8 valence electron, while there will be the 2 remaining valence electron on the xenon. Hence, the total number of lone pair of electron on the xenon, that is on the central atom, is equals to 1, as the one lone pair contain the 2 electron. Now, again use a simple formula which will decide the type of hybridization. That formula is the total number of a atom attached to this central atom plus the total number of a lone pair of electron on the central atom. So, the total number of atom attached to the central atom is equals to 6, and the total number of a lone pair of electron on the xenon hexafluoride is equals to 1. Hence, the number comes to be 7. Hence, the type of hybridization of a xenon atom in a xenon hexafluoride molecule will be the sp3d3. Again, just find out, we know that here we are using the 1s atomic orbital, 3p atomic orbital and the 3d atomic orbital. 1s plus 3p, that means 1 plus 3 equals to 4, and 3d. So, 4 plus 3 equals to 7. So, this number will be the 7. Hence, the type of hybridization of a xenon in the xenon hexafluoride molecule is sp3d3. Now, let us consider the next example, that is Xenon Oxytetrafluoride molecule. So, the molecular formula will be the ZeOF4. So, here again the central atom will be the xenon. Now, let us consider the electronic configuration of the xenon. We know that xenon atomic number 54. So, its electronic configuration will be the krypton 36, 5s2 and 5p6. So, 5s and the 5p contribute to the valence shell. Hence, the total number of a valence electron in that valence shell is equals to the 8. So, total number of a atom attached to the central xenon atom is equals to 5, as it contains the 4 fluorine atom and the 1 oxygen atom. Now, here you have to use a one trick. Again, just find out the structure that I have shown for the Xenon Oxytetrafluoride. Here you can observe that the 4 fluorine is attached to the xenon by the single bond, while the oxygen atom, which is a single, attached to the xenon by the double bond. So, here out of the 8 valence electron, 4 valence electron will be used by the each 4 fluorine atom to form a single bond with a xenon. Hence, out of 8, 4 valence electron will be used by the 4 fluorine atom, while the 1 oxygen atom use the 2 electron to form the double bond with the xenon. So, 4 by the fluorine, 2 by the oxygen. Hence, out of 8, the total valence electron used for the formation of your xenon oxyfluoride molecule will be the 6. So, out of 8, 6 are used to form bond. Hence, the 2 electrons will be remain. Now, these 2 electrons are the remaining valence electron on the xenon atom. As the 2 electron, hence the lone pair of electron on the central atom is equals to 1. Again, use our simple formula. Here, the total number of atom attached on the central atom plus total number of a lone pair of electron on the central atom. So, in the xenon oxyfluoride molecule, the total number of atom attached to the central atom, that is to the xenon, is equals to 5, 4 fluorine plus 1 oxygen, while the total number of a lone pair of electron on the xenon is equals to 1. Therefore, 5 plus 1 will be equals to 6. So, the number comes to be 6. Therefore, the type of hybridization in the xenon oxytetrafluoride molecule is sp3d2 hybridization. So, here 1 s atomic orbital is used, 3 p atomic orbital is used and 2 d atomic orbital is used. So, here 1 plus 3 plus 2, that will be equals to 6. So, the type of hybridization in the xenon oxytetrafluoride molecule will be the sp3d2 hybridization. Now, again let us consider the next example. So, here I have taken xenon dioxy difluoride molecule. So, its molecular formula is ZeO2F2. The central atom is again xenon. The electronic configuration of this central atom, that is xenon, will be equals to krypton 36, 5s2 and 5p6. So, the total number of valence electron on the central xenon atom is equals to 8, as the 5s and 5p contribute to the valence shell. Hence, the total electron present in this atomic orbital will be equals to 8. So, here you have to note one important point. I have shown the structure of the xenon dioxy difluoride molecule. Here you can observe that the 2 fluorine attach to the central xenon by the single bond, while the 2 oxygen atom attach to the xenon by the double bond. So, out of 8 valence electron, the 2 fluorine will use only 2 valence electron as they form a single bond, but here the each oxygen atom will use the 2 valence electron of a xenon. So, here the 2 oxygen atoms are attached. So, each oxygen atom using the 2 electron, hence the 2 oxygen atom will use the 4 electron. So, 4 plus 2 electron which is utilized by fluorine, that will be equals to 6. Out of 8 valence electron, 6 are utilized by the 2 oxygen atom and the 2 fluorine atom. Hence, the remaining valence electron will be equals to 2. If the remaining valence electron is 2, then the total number of lone pair of electron on the xenon is equals to 1. Again, one point you must note that in the xenon dioxy difluoride molecule, the total number of atom attached to the xenon is equals to 4. So, now again use a simple formula. Here, the total number of atom attached to the central atom plus the total number of a lone pair of electron on the central xenon atom. So, here that number, the total number of atom attached is equals to 4. The total number of a lone pair of electron is equals to 1. Hence, the number is comes to be 5. If the number is 5, then the type of hybridization of a xenon in xenon dioxy difluoride will be sp3d hybridization. Again, you can cross verify it. Here you know that. So, here 1 s atomic orbital is used, 3 p atomic orbital is used. So, 1 plus 3 equals to 4 plus 1 d atomic orbital is used. Hence, 4 plus 1 is equals to 5. The hybridization will be the sp3d hybridization. So these are the few challenging examples that we have discussed in this video. Now in the next video we will again discuss the few challenging example. Thank you so much for watching this video. See you in my next video.